Good morning. Good morning, everybody. I am ready to get started on Chapter 9. Chapter 9 has to do with impulse and momentum. It's entitled Momentum. It's a new quantity that we haven't dealt with yet, but turns out to be very useful. Everything starts up here in the upper left-hand corner of the board. So, uh, Chapter 9, Momentum. The first topic covered is impulse. Now, impulse has the symbol capital J. This is the symbol used for impulse. And impulse is defined as the force applied to an object times the time that the force is applied. So the units for impulse are going to be newtons times seconds, force units times time units. So a newton times a second is the unit for impulse. So force times time, it's applied, that's the basic definition. Now I've got an example problem where we calculate the impulse exerted on an object. So down here I've got a picture of somebody pushing a box. Okay, can you see that okay? Yeah. So you apply 20 newtons of force for 15 seconds. So this person pushes the box for 15 seconds with a force of 20 newtons. And what you want to do is solve for the impulse on the box. So to do that, you take the force and multiply it by the time the force is applied. The force is 20 newtons, the time it's applied is 15 seconds. So the total impulse on the box is 300 newton seconds. To the right, it's a vector quantity. There's a direction associated with impulse because impulse is directly related to force, and force is a vector quantity. So the impulse on an object points in the same direction as the applied force on the object. And also, there's a graphical representation of impulse, and I've got that up here. Now, this graph represents the impulse exerted on the box in this problem that I just talked about. So notice that I've got force on the vertical axis and time on the horizontal axis. Vertical axis, force is measured in newtons. Horizontal axis, time is measured in seconds. And here I've got a constant value of 20 newtons applied across a time of 20 seconds. So if you were to find the area of this rectangle, it would be the width times the height, so that would be 15 seconds times 20 newtons, which gives you the 300 newton seconds that we calculated over here. And so the area inside that box is 300 newton seconds, or the impulse applied. Now we're going to do the same problem again on the same box, but this time we're going to apply 50 newtons for 6 seconds. So now push the box with 50 newtons of force for 6 seconds. If we redo the calculation for the new impulse, J2, it's going to be the force applied, 50 newtons, times the time that it's applied, 6 seconds. Once again, we get 300 newton seconds to the right. So these impulses are the same. So, you know, it's a different problem, different amount of force, different amount of time, yet we get the same value for impulse. So maybe impulse has some deeper meaning that we haven't talked about yet. We're going to get there. So now I come down here, and here's Newton's second law, F equals ma. Now, if the acceleration is constant, which in this case it is, at least during the time the force is applied, it's constant in either case, then we can apply constant accelerated motion. And here's the first equation of constant accelerated motion. V final is equal to V initial plus AT. And I've rearranged it to solve for A. A is going to be equal to V final minus V initial divided by the time. Now we're calling it delta t. It's just the amount of time that the acceleration occurs. So we're going to take this way of representing acceleration, plug in here, and if we do that, we'll get this. M times the quantity V final minus V initial divided by delta t. If we distribute the mass into each one of these velocity factors, then we get mv final minus mv initial divided by delta t. And now if we multiply both sides of this equation by delta t, the delta t comes over here, and we end up with the force times the time the force is applied is equal to mass times the final velocity minus mass times the initial velocity. So you can say that J, the impulse, which is the force times the time the force is applied, acting on the box is going to be its mass times its final velocity minus mass times its initial velocity. And here, this m times v is an important quantity that we give its own name to, and that is what momentum is. The momentum of an object is its mass times its velocity. And it is a vector quantity. We use lowercase p to represent momentum, and it points in the same direction as the velocity of the object. So you can rewrite the impulse equation as the impulse is equal to the change in velocity of an object. Because change in velocity is going to be the final, change in momentum is going to be the final momentum minus the initial momentum. Now, here's the impulse equation. Force times the change in time the force is applied is equal to the mass of the object times its change in velocity. So this is the impulse momentum theorem. And by the way, this is really just a restatement of Newton's second law, right? You can divide through by delta t, and you've got Newton's second law. F is equal to m delta v over delta t, which is just a, acceleration. So now we're going to give this box over here at the beginning of the first part of the problem, we're going to give it a mass now. The mass is going to be 5 kilograms for the box. Now if we solve for delta v here, the change in the speed of the box, well, that's going to be equal to the force applied times the time it's applied divided by the mass. And in both cases, that would be 300 Newton seconds divided by 5 kilograms, which works out to 60 meters per second. So in both cases, whether you apply a small amount of force for a long time or a larger amount of force for a shorter time, the total change in the velocity of the box was 60 meters per second. So there was something similar about the two problems. The change in velocity was the same, and we used the impulse equation to solve for that.